Hi, I'm Andrew.
I'm Alexa.
I'm Sarah.
For our project, we chose Hydrodynamic Levitation. The main idea is basically it's a ball spinning on top of a stream of water.
Specifically for our project, we chose to look at the mass of the ball versus the velocity of the water stream when it touches the ball.
So we used two different sized balls. We have a dirty wiffle ball and a clean wiffle ball, and we measured how high they levitated.
This was the first ball that we used. It was the smaller and cleaner of the two. Before we started the levitation experiment, we needed to determine its diameter and its weight for our calculations later on. To measure the diameter of the ball, we used a dial caliper so that we could be as precise as possible. To figure out the weight of the ball, we used a food scale that I had lying around my house. We found that this ball's diameter was 2.516 inches. For the weight, it was determined that this ball weighed 10 grams. Next, we had to repeat the same process with the larger ball, which had more dirt on it. We used the same tools for this ball. We determined that the diameter was 2.737 inches. The weight of this ball turned out to be 17 grams. Now for our setup. After some trial and error, we determined that it was extremely important for the water to be shot straight up vertically in order for the ball to levitate on it properly. Getting the nozzle to be perfectly level was much harder than you might expect. For our experiment, we determined that it would be best if we hung a board off of a deck and counterbalanced it with a heavy rock. We then used wooden shims to shove underneath the rock to make sure that the nozzle was perfectly level so that the water would shoot straight upwards. We drilled a hole through the board so that we could put the hose that was supplying the water through it. Then we screwed on the nozzle on the other side of the board to attach it to the hose. The nozzle was one of the most important parts as we needed a perfect stream of water for the ball to float on. In order to keep our calculations as simple as possible, we wanted to start measuring at the point at which the water left the nozzle. This way, we wouldn't have to do any extra math when finding out the height of the ball, because the number that the ball was at on the tape measure would be the distance away from the nozzle. To get the tape measure high enough, we set it on a ladder and made it perfectly vertical, so then we would have a good background measuring device while the ball was levitating. Here's our first ball, the smaller of the two. As you can observe, we found that the average height that it levitated at was around 61 inches. Here are the results for ball 2. We found that the average height it levitated at was around 45 inches. Another important part of our data was finding the water pressure. To find this, we filled a 5-gallon bucket immediately after the experiment finished without changing the water pressure. So then we could use equations to calculate the water pressure. We stopped the time as soon as the bucket overflowed, and we found that it took 5 minutes and 40 seconds to fill.
These are our calculations for our project. As you can see in the diagram, we set the datum at the point where the water leaves the nozzle, and that's also point 1. For point 2, we set that at where the water meets the ball. For the calculations, we used Bernoulli's equation for P1 and P2, and we solved that to find V2. Using this equation, we applied it to both of the cases and got the velocities for where the ball meets the water. Our results for our project concluded that The greater distance from the nozzle to the ball meant that the velocity would be lower where the ball touched the water. Another conclusion that we came to was the ball with the larger mass had to be at a lower height.